For most of the 20th century, Antarctica was treated as a dead continent in the most literal sense, a place so uniformly hostile that scientists assumed nothing meaningful could exist beneath its ice sheet beyond a few kilometers of compressed snow and eventually bedrock. The ice covering Antarctica averages nearly 2 kilometers in thickness and exceeds 4 kilometers in some locations, an amount of frozen water so large that if the entire ice sheet melted, global sea levels would rise by roughly 60 meters. Given that scale, it made intuitive sense to assume the ice simply sat on rock, an inert cap over an inert surface with nothing happening underneath except the slow grinding of glacial movement. That assumption turned out to be wrong in ways that have reshaped multiple fields of science at once, and the story of how researchers discovered this is one of the more genuinely unsettling scientific narratives of the last several decades, not because anything supernatural happened, but because what they found raises questions nobody has fully answered yet about life, about climate, and about what else might be sitting beneath ice sheets on this planet and possibly others. The first hint that something was different came from radar surveys conducted by Russian scientists in the 1970s, flying instruments over the ice near their Vostok research station in East Antarctica. Ice-penetrating radar works by sending radio waves down through ice and measuring how long it takes for the signal to bounce back. And different materials reflect radar in distinct ways, allowing researchers to distinguish between solid ice, bedrock, and liquid water based on the reflection pattern. When Russian and later British researchers analyzed data from flights over Vostok, they noticed a section of exceptionally flat, smooth radar reflection roughly the size of Lake Ontario, a signature that made far more sense as a body of liquid water than as bedrock. The implication was almost impossible to accept at first. Beneath 4 kilometers of ice, in a place where surface temperatures regularly drop below negative 60 degrees Celsius, there appeared to be an enormous lake of liquid water, sealed away from the outside world. For a length of time nobody could immediately estimate. Confirmation took years of additional survey work, but by the 1990s, Lake Vostok was accepted as real, and it turned out to be merely the first of what scientists now know to be an entire network of subglacial lakes scattered beneath the Antarctic ice sheet, with current counts exceeding 400 distinct lakes identified through radar and satellite surveys, connected in some cases by river-like channels that move water between them beneath the ice. The existence of liquid water beneath an ice sheet, that cold seems contradictory until you understand the physics involved, and once you do understand it, the picture becomes almost stranger rather than less so. Ice, several kilometers thick, and acts as an extraordinarily effective insulating blanket, trapping geothermal heat rising from the Earth's interior and preventing it from escaping into the atmosphere above. At the same time, the sheer weight of that much ice generates enormous pressure at the base of the sheet, and pressure lowers the melting point of ice, a basic physical principle that means ice under extreme pressure can remain liquid at temperatures that would freeze it solid at normal atmospheric pressure. Combine trapped geothermal heat with pressure-lowered melting points, and you get liquid water existing in a stable state at the base of an ice sheet, insulated from the frozen world above by kilometers of ice, sitting in near total darkness, at pressures far exceeding anything found in a typical ocean environment, and cut off from any direct contact with the atmosphere for a period of time that, in the case of Lake Vostok specifically, researchers estimated at somewhere between 15 and 25 million years of isolation. That number bears repeating because of how strange it is. Lake Vostok has existed as an enclosed, isolated body of water since before humans, before most modern mammal species, sealed away under ice through multiple ice ages and interglacial periods, effectively representing one of the most isolated environments accessible anywhere on the planet's surface, comparable in some ways to conditions scientists imagine might exist on icy moons elsewhere in the solar system. Isolation of that duration raises an obvious question that drove much of the subsequent research. Could anything be alive down there, and if so, what would millions of years of complete isolation do to it? Answering this question required actually drilling into the lake, which itself became one of the most technically fraught and scientifically debated projects in polar research history. Russian scientists spent decades drilling an ice core at Vostok Station, initially for climate research purposes unrelated to the lake, since ice cores preserve a chemical record of past atmospheric conditions that scientists use to reconstruct historical climate patterns, going back hundreds of thousands of years. As the drilling approached the boundary where ice met the lake water below, researchers faced a genuine dilemma, because drilling fluid used to keep the borehole from refreezing during the process risked contaminating the pristine lake with kerosene and other chemicals, potentially destroying the scientific value of the very discovery they were trying to study, while also raising concerns about introducing surface microorganisms into an ecosystem that might have evolved in complete isolation for millions of years. International scientific bodies debated protocols extensively, and Russian researchers eventually developed a method intended to let lake water rise into the borehole and freeze in place, allowing them to retrieve a frozen sample of lake water on a subsequent trip, rather than directly puncturing into open water and risking contamination in both directions. When Russian scientists finally announced in 2012 that they had reached Lake Vostok's surface, breaking through after roughly 2 decades of drilling, the achievement was framed by some media outlets in dramatic terms, comparing it to reaching another planet. And in fairness to that framing, the environmental conditions really do bear meaningful resemblance to what astrobiologists expect to find on icy moons like Europa or Enceladus, both of which are believed to harbor liquid oceans beneath thick ice shells, heated not by sunlight but by tidal forces and radioactive decay, exactly the kind of environment where scientists suspect life might exist without ever having been exposed to sunlight or a conventional atmosphere. What researchers found in the recovered ice samples was genuinely intriguing without being sensational in the way some coverage implied. Analysis of the frozen accretion ice, the layer that forms when lake water freezes onto the bottom of the ice sheet, revealed genetic material from thousands of distinct types of bacteria, along with signatures suggesting the presence of more complex organisms in some samples. Some of these genetic sequences matched known extremophile bacteria, organisms adapted to survive in environments most life would find lethal, including species related to bacteria found near hydrothermal vents, in other extreme, nutrient-poor environments on the planet's surface. Other sequences proved harder to classify, not matching cleanly with known organisms in existing genetic databases, which researchers interpreted cautiously, given the very real risk of contamination from drilling equipment, laboratory handling, or the kerosene-based drilling fluid itself, all of which could introduce foreign genetic material that might be mistaken for something novel and native to the lake. This contamination concern deserves serious attention because it explains much of the ongoing scientific caution around subglacial lake research. And it's worth understanding clearly rather than glossing over, since it complicates any simple narrative about discovering ancient alien-like life. Modern molecular biology techniques are so sensitive that they can detect vanishingly small amounts of genetic material, which is generally an enormous advantage for research, but becomes a serious liability when working with samples that might contain even trace contamination from human sources, laboratory reagents, or the environment surrounding a research station occupied by scientists, mechanics, and support staff for months at a time. Distinguishing between genuine ancient lake organisms and contamination introduced during drilling, sample handling, or laboratory analysis requires extremely careful controls, and even with those controls in place, some ambiguity in early results was inevitable given how novel and technically difficult this kind of research was. Subsequent research efforts, including drilling into other subglacial lakes like Lake Whillans and Lake Mercer, which are considerably shallower and easier to access safely than Vostok, used improved clean access protocols specifically designed to minimize contamination risk, and these efforts have produced results that researchers consider more scientifically solid. Drilling into Lake Whillans in 2013, for example, using a hot water drill system, designed with strict contamination controls, recovered water and sediment samples that revealed a genuinely active microbial ecosystem, with researchers estimating hundreds of thousands of individual microbial cells per milliliter of lake water, representing an ecosystem thriving in complete darkness beneath 800 meters of ice, supported entirely by chemosynthesis rather than any input from sunlight. The chemosynthesis angle matters enormously here, because it echoes one of the most significant discoveries in modern biology, the hydrothermal vent ecosystems found on the deep ocean floor starting in the late 1970s, which proved that entire complex food webs could exist independent of sunlight, built instead around bacteria that convert chemical energy from minerals into usable biological energy. Subglacial lake ecosystems appear to work on a broadly similar principle, with microbial communities deriving energy from chemical reactions involving minerals and rock and sediment beneath the ice, rather than from photosynthesis, since no sunlight has reached these environments in extremely long time frames, in some cases many millions of years. This matters beyond the immediate question of what lives in Antarctic lakes specifically, because it reinforces a broader pattern that keeps recurring throughout deep environment research on this planet. Life finds ways to establish itself and sustain complex ecosystems using energy sources far removed from sunlight, in conditions of extreme cold, extreme pressure, and complete isolation, using biochemical strategies that continue to surprise researchers each time a new environment gets examined closely enough. Every confirmation of a functioning ecosystem in an environment and previously assumed too hostile for life adds weight to the argument that life, at least at the microbial level, may be far more tenacious and adaptable than assumptions built primarily around surface conditions would suggest. Beyond the question of microbial life, subglacial Antarctic research has produced findings that are, in a different sense, genuinely alarming to climate scientists. And this is arguably where the word terrified applies most literally to the reactions of researchers working in this field. Understanding what lies beneath the ice sheet matters enormously for predicting how that ice sheet will behave as global temperatures rise. And several discoveries in this area have complicated climate models in ways that suggest previous predictions may have underestimated how quickly certain sections of Antarctic ice could destabilize. Subglacial lakes and the water channels connecting them appear to play a significant role in ice sheet dynamics because liquid water at the base of an ice sheet acts as a lubricant, reducing friction between ice and bedrock and allowing ice to slide more easily toward the ocean. Researchers studying satellite data have observed subglacial lakes periodically draining and refilling in events that can move enormous volumes of water beneath the ice over relatively short timeframes, sometimes just weeks, and these drainage events appear correlated with measurable changes in the speed at which overlying ice flows toward the coast. This creates a feedback dynamic that climate models built primarily around surface temperature and ice melt had not fully accounted for in earlier iterations. Since a climate doesn't just melt ice from the surface and from contact with warming ocean water at glacier edges, it may also be capable of altering subglacial hydrology in ways that further destabilize ice flow from below, independent of and in addition to surface melting processes. The discovery of extensive subglacial water networks, including rivers running beneath the ice sheet that can be kilometers long, has forced researchers to reconsider how quickly certain glaciers, particularly in West Antarctica, might respond to continued warming. The Thwaites Glacier, sometimes referred to in media coverage by the nickname the Doomsday Glacier because of the sheer scale of sea level rise its collapse could eventually cause, sits atop bedrock that in places lies below sea level, a configuration that makes it particularly vulnerable to a phenomenon called marine ice sheet instability, where warm ocean water intruding beneath the glacier's floating ice shelf can trigger a self-reinforcing retreat that continues even if atmospheric warming were to stop entirely. Subglacial hydrology discoveries add another layer of complexity to predicting how this process unfolds, because water moving beneath the glacier interacts with this marine instability dynamic in ways that aren't yet fully incorporated into every climate model. And researchers studying the region have expressed genuine concern that combined effects from ocean water, intrusion, subglacial water flow, and structural weaknesses discovered in the ice shelf itself could mean Thwaites Glacier becomes unstable on a faster timeline than earlier, more conservative model projections suggested. Total collapse of Thwaites Glacier alone could raise global sea levels by roughly 65 centimeters, and because it acts as a partial barrier, holding back a much larger ice shelf, structural surveys have added their own unsettling findings to this picture. Researchers using ice-penetrating radar and other remote sensing techniques to examine the underside of ice shelves, the floating extensions of glaciers that extend out over the ocean and help stabilize the ice sheet behind them, have discovered extensive crevasse and fracture networks in locations that models had not predicted, along with evidence of warm ocean water actively carving channels into the base of these shelves from below, a process that is difficult to observe directly because it happens underneath ice, in ocean water, in one of the difficult environments on the planet for research vessels and equipment to access safely. Some surveys have found that ice shelves considered structurally important for holding back glacial flow are more compromised, riddled with more internal fracturing and basal melting than surface observations alone would suggest, which matters because ice shelf collapse tends to happen suddenly rather than gradually. Once structural weaknesses reach a critical threshold, a pattern already observed directly when the Larsen B ice shelf on the Antarctic Peninsula disintegrated over the course of just a few weeks in 2002, an event that surprised scientists with its speed, even though the shelf had shown gradual signs of thinning for years beforehand. Antarctica has also produced discoveries that touch more directly on the history of life and climate on this planet, adding depth to why researchers describe some of these findings as unsettling rather than simply interesting. Ice cores drilled through the ice sheet, including at Vostok Station and other research locations, preserve tiny bubbles of ancient atmosphere trapped as snow compacted into ice over hundreds of thousands of years, allowing scientists to directly measure historical concentrations of carbon dioxide and other gases going back roughly 800,000 years, and in some more recent ultra-deep drilling projects considerably further than that. These ice core records have provided some of the strongest direct physical evidence linking atmospheric carbon dioxide concentrations to global temperature across multiple ice age cycles. And what makes current findings concerning to researchers is how far current atmospheric carbon dioxide levels now exceed anything recorded in these ancient ice records. Meaning, humanity has pushed the atmosphere into a chemical state that hasn't existed at any point captured by this 800,000 year physical record, and possibly not for several million years based on other geological proxy evidence. Reading that history directly from ice cores rather than from indirect geological proxies, gives researchers a level of confidence in this conclusion that is difficult to dismiss. And confronting that record directly, watching an unambiguous physical record of Earth's climate history and seeing current conditions, diverge so sharply from anything in that record, is part of what researchers in this field describe as a genuinely sobering experience. Beneath all of the ice sheet research also lies an entire landscape that remained completely unknown until relatively recently, revealed through advances in ice-penetrating radar, gravity measurements from satellites, and other remote sensing techniques capable of mapping bedrock topography without any direct physical access. Researchers have identified a canyon system beneath the ice in East Antarctica, dubbed by some researchers, informally in comparison to other major canyon systems, that appears to be over 1,000 kilometers long and, in places, deeper than the Grand Canyon, entirely hidden beneath the ice sheet and invisible from the surface or from space using conventional optical imaging. Mountain ranges comparable in scale to the European Alps, called the Gamburtsev Mountains, sit entirely buried beneath the ice in East Antarctica, discovered initially through seismic surveys and confirmed through subsequent radar mapping, and their existence puzzled researchers for years because the mountains appear geologically old, yet mountain ranges of that age typically erode down to nothing over the timescales. Involved, unless something preserved them, with current theories suggesting the ice sheet itself may have formed early enough to essentially freeze the mountains in place, before major erosion could occur, preserving a landscape that would otherwise have worn away entirely. Discoveries like these underscore just how much of Antarctica's actual geography remains hidden beneath a featureless white surface that gives no external hint of the canyons, mountain ranges, lakes, and rivers concealed below, and how recently in scientific terms this hidden landscape has even begun to be mapped in any detail. Taken together, these findings explain why the phrase terrified, while dramatic, captures something real about how researchers in this field describe their reactions to what continued investigation of Antarctica keeps revealing. It isn't that scientists found a monster or something threatening in a direct, immediate sense. It's that Antarctica turned out to be a far more dynamic, far more biologically active, and far more structurally fragile system than the frozen, static picture most people carry in their heads would suggest, and every layer of additional research seems to reveal further complexity rather than settling into a simpler, more predictable picture. A continent once assumed to be an inert block of ice sitting quietly atop equally inert rock turns out to conceal hundreds of interconnected lakes, active microbial ecosystems surviving on chemical energy in total isolation from sunlight for millions of years, structurally compromised ice shelves being actively undermined by warm ocean water in ways not fully captured by existing models, subglacial rivers capable of accelerating glacial flow. Toward the ocean, hidden canyon and mountain systems as large as some of the most famous geological features on other continents, and a direct physical climate record showing that current atmospheric conditions have no precedent across the entire span of time that ice core data can access. None of these findings individually amounts to a single dramatic monster under the ice, but collectively they paint a picture of a continent whose interior behavior remains far less understood and considerably more volatile than the calm white expanse visible from the surface would ever suggest, and that gap between appearance and underlying reality is precisely what continues to unsettle the researchers spending their careers trying to close it.